Have you ever wondered how the most powerful computer vision models like YOLO could run on a phone while it used to require lots of compute power? If you've been in the field for a while, you probably remember the early days where we played around with architectures like VGG, ResNet, or DenseNet and trained those models with ImageNet or smaller datasets to get our results. Back then, it was hard to imagine how far we'd come to run advanced vision models on such tiny devices. Let's dive into a short evolution of computer vision and explore how these models are now being adapted to run efficiently on small devices for maximum impact with Qualcomm, our partner for this video. In the early days, the technology was quite basic. We dealt with simple computational architectures focused on applying mathematical filters that scanned images pixel by pixel. It was all about edge detection algorithms like Sobel and Canny to identify where one object ended and another began. As time progressed, researchers wanted machines to not just detect edges, but to recognize objects, like cars or faces. Methods like SIFT and others emerged, allowing for more detailed feature extraction by stacking layers of filters to process images in a more complex way. A big breakthrough came in 2001 with the Viola-Jones algorithm, one of the first real-time face detection systems, and in 2012 the field transformed with the ImageNet moment. The introduction of AlexNet, a convolutional neural network, or CNN, revolutionized computer vision by using raw pixel data and hierarchical learning to classify images with unprecedented accuracy. This changed the game, especially for tasks like image classification. As classification models improved, the focus shifted to object detection, not just identifying if an object is in an image, but also locating it, and, ideally, locating these objects in real time, which used to mean 20 frames processed per second, and now over 100. This is where YOLO, or You Only Look Once, introduced by Joseph Redmond in 2016, made a lot of noise. And I wasn't even around back then to celebrate, having started in the field in 2018. YOLO framed object detection as a single regression problem, predicting both the class and the location of objects in one go, making it incredibly fast and ideal for real-time applications like self-driving cars or drones. Since then, each version of YOLO improved significantly. YOLO v2 introduced batch normalization and anchor boxes, allowing it to handle higher resolution images. YOLO v3 predicted objects of 3 different scales and switched to a more efficient backbone network. Then came YOLO v4, the first version I covered on my channel, which is also one of the first videos I made. It optimized the model for both speed and accuracy, making it ideal for devices from edge systems to high-power servers. By the time YOLO v6 and YOLO v7 arrived, they had introduced anchor-free approaches, self-distillation, and real-time pose estimation, pushing the boundaries of what was possible with object detection. YOLO v7 introduced a trainable bag of freebies approach that boosts detection accuracy by optimizing the training process without increasing inference time, and they also set a new state-of-the-art for real-time object detection, achieving an impressive accuracy of 56.8% at a frame rate as high as 161 FPS, or even more with other versions on a GPU like the V100, surpassing even transformer-based detections like SwinL Cascade Mask RCNN by over 5 times in speed while being 2% more accurate. YOLO v7 incorporates efficient model scaling and the extended ELAN or Efficient Layer Aggregation Networks architecture, which allows the model to learn a wider variety of features by improving feature aggregation and gradient flow, all without adding extra computational overhead. Compared to earlier models like YOLO v4, YOLO v7 reduces the number of parameters by 75% and reduces computation by 36% while delivering a higher accuracy. Even the smaller version, YOLO v7 Tiny, shows significant improvement with over 10% better accuracy compared to YOLO v4 Tiny, while maintaining faster inference speeds. Today, YOLO models are used everywhere, from self-driving cars detecting pedestrians to smart home cameras recognizing faces, and even in retail for tracking inventory. One of the biggest shifts we see is the move toward on-device deployment. Running models directly on devices has huge benefits. It's cost-effective because it reduces reliance on cloud computing, it's efficient as it uses the device's local power for faster processing, and it's private since data doesn't leave the device, improving security. On-device models can also be easily personalized for specific user needs without needing cloud updates. So how do these models actually get deployed on devices? This is done through device-in-the-loop deployment, where models are optimized and set on target devices. Qualcomm's AI Hub automates much of this process, making deployment models like YOLOv7 on edge devices straightforward. Here's how it works. First, you'll want to get your trained model. Then, it goes through a process called graph capture, which is basically like tidying up its operations. This step simplifies everything, combining tasks and cutting out the unnecessary bits. The result? A smoother, faster model, especially when running on hardware like mobile GPUs, TPUs, or NPUs. In the end, your model is quicker and uses fewer resources, making it perfect for low-power devices while still getting the job done efficiently. After you've trained a model or got a pre-trained model, the next step is to compile it specifically for the hardware you'll be using, whether that's mobile GPUs, NPUs, or edge devices. Think of it like translating the model into a language that the device understands so it can run smoothly and efficiently. Different devices have their own limits, like memory or power. By compiling the model for a specific device, you make sure it uses the hardware efficiently, which is especially important for things like mobile or embedded systems that don't have a lot of resources to spare. Once compiled, you'll want to double-check that the model's computations are still accurate. In other words, the outputs should match what the original model produced before it was optimized for the hardware. This is important because optimizations can sometimes tweak things in unexpected ways, and you want to make sure it's still giving correct results. For example, if you quantized a model to reduce precision and work with integers instead of float points to save compute, you will want to study the resulting outputs to ensure the results and accuracy remains intact. After confirming everything is working as expected, it's time to see how well the model performs on the actual device. This involves testing for things like inference speed, which is how fast it makes predictions, memory usage, and power consumption to make sure it's efficient. Even if the model is accurate, it needs to perform efficiently on the target device. For instance, on mobile devices, if the model uses too much memory or power, it can cause battery drain or system lag. By evaluating the model's performance, you ensure that it meets the constraints and performance goals of the specific environment, providing a smooth user experience. If there are any hiccups, this is where you fine-tune things, either tweaking the model itself or adjusting the hardware settings so that it runs optimally in real-world conditions. We teach about all these improvement steps for advanced models in our recent book, Building LLMs for Production. Once everything is validated and optimized, you are ready to deploy the model. At this point, it's fully operational and can start making predictions or decisions within the application you've designed it for, working seamlessly on the target hardware. This whole process ensures the model runs smoothly on devices and it can be adjusted in a feedback loop if performance improvements are needed. Now, let's actually do it with the YOLOv7 model and look at how easy it is to set up and run a model. First, you'll need to configure your Qualcomm AI Hub API key. After that, select the model you want to run, choose the target device, compile it, and deploy it on cloud-hosted edge devices. The entire process ensures your models are fast, efficient, and optimized for a specific device, whether you are working with image segmentation, object detection, or any other real-time task. You now need to set up and run the model. It's also super easy with Qualcomm AI Hub for tasks like vision, audio, and speech directly onto edge devices. They offer over 100 ready-to-go models for everything from vision to text, which you can get running on Snapdragon and Qualcomm-powered devices in just minutes. You also find all the open source recipes you need on GitHub and Hugging Face to help you get started quickly. Alright, let's deploy the YOLOv7 model. When you visit the models page, you'll see key details like inference time, which help you assess how fast the model will run on your device. You'll also find compatibility information to ensure it works smoothly on specific mobile devices and chipsets. Additionally, understanding the resolution and model size helps you strike a balance between accuracy and performance, ensuring your app runs efficiently without compromising quality. To begin, install the Qualcomm AI Hub library from PyPy. This library is essential for optimizing, profiling, and validating your models. Next, sign in to Qualcomm AI Hub using your Qualcomm ID. Once logged in, click on your ID at the top right corner, head to Settings, and grab your API token from the API token section. Once that's done, check that your API token is installed correctly by listing available devices with this line. Now, install the YOLOv7 model through the Qualcomm AI Hub. After that, you'll need to export the model to a mobile device. This is the model compilation step we discussed earlier. Once compiled, you'll find the model in your profile under Compiled Models. You'll also have the option to visualize the model in the AI Hub, which will show the graph capture process. Finally, you can run an inference job to see how well the model performs on your device. It was as simple as that. Please let me know in the comments or ask in the Qualcomm's Slack channel linked below if you run into any issues replicating this work. I also added the notebook and more information on Qualcomm's libraries in the description below. Try it out and let me know what application you create. This is a really good project to build your portfolio. In conclusion, the evolution of computer vision has been remarkable, from simple edge detection to advanced models like YOLO, and here YOLOv7, and language models like Meta's recent Llama 3 smaller distilled models. These advancements have made real-time applications such as self-driving cars, smart cameras, and medical imaging more powerful and efficient. The shift toward on-device deployment is a game changer, offering speed, privacy, and cost-effectiveness by minimizing cloud dependency. As models continue to become more versatile and easier to deploy, especially with tools like Qualcomm's AI Hub, we are moving toward a future where AI-powered devices can operate independently, providing real-time intelligence at our fingertips. Whether it's fast object detection with YOLO, precise segmentation with SAM, or language with Llama, the potential for AI on edge devices is super exciting. I'll leave you with a very cool quote from Andrzej Karpathy along that way.
And I think we just need to get to the cognitive core. And I think the cognitive core can be extremely small. And it's just this thing that thinks. I think even a billion suffices. We'll probably get to that point. And the models can be very, very small. And I think the reason they can be very small is fundamentally, I think, just like distillation works. It may be like the only thing I would say. Distillation is where you get a really big model or a huge amount of compute or something like that, supervising a very small model. And you can actually stuff a lot of capability into a very small model.